Hello, this is the luckiest maths teacher in the world. Today we're looking at independent and mutually exclusive events. We're going to learn what they are and we're going to apply these principles to probability calculations. But first we need to look back at Venn diagrams. So I'll now draw one for you. So this is a Venn diagram like we learned last lesson, and I'll call the two sets A and B. Now recall that the union of A and B, which I write like this, A union B, is all of this area that I'm shading now. So anything that is in any part of either circle is a member of A or B, or both. A union B. So what we're going to do is look at how to calculate the probability that an event is in A union B. We're going to look at how we find the probability that of two events, either or both of them occur, if we know the probability of each. Now, it's a very simple formula. So, I'm quickly going to get rid of these lines. Now, there's a very simple formula. So, the probability of A union B, that is A or B or both happening. So it's like so probability is about proportion. It's the proportion of numbers that are in, the proportion of events that are in each of these sets A and B. So it's this proportion here, which is A, plus this proportion here, which is B. So that's just the probabilities. Proportion and probability are the same thing. So it's just adding together the two probabilities. But the astute of you will note that I've actually double counted this part in the middle. See, I included that when I included probability of A, and then I included it again when I included probability of B. So those events in the middle would get counted twice. So what I need to do is I need to subtract the probability that an event is in the middle, the probability that it is in A and B, so that I'm not double counting it. Okay, so this is the formula here. Please pause and write it down if you need to. The probability of A or B equals the probability of A plus the probability of B minus the probability that both happen. So let's do a quick example. Let's say that I roll a normal six-sided die, and I want to know the probability that the number I get is either even or a multiple of 3. I'm just going to write mult for short. Okay? So I can think, now I have probability of one event or the other, I can think of probability of even, so that will be my event A, and then multiple of 3 will be the event B. So I just use that formula to figure this out. I'm just going to show you on the Venn diagram, so I'll just quickly erase all the markings on the Venn diagram. Okay, so let's go ahead and write the events A and B. So to get in event A, how I roll an even number on a six-sided dice is I could get a 2, or I could get a 4, or I could get a 6. And to achieve B, to be in B, to get a multiple of 3 while I'm rolling die, I could get either 3 or 6. Okay, now each of these events has probability of 1/6. There's a 1/6 chance I'll get a 2. There's a 1/6 chance I'll get a 4. Same with 6, 3, and 6, right? So you can see here that there are 1, 2, 3, 4, 5 ways for my event to occur. So I'm just adding 1/6, 1/6, 1/6, which is A. Its probability is a half. 3/6. The probability of B is 2/6. Excuse me, or a third. So the probability of getting A or B is just adding all these together. A sixth plus a sixth plus a sixth, and then adding it again. So there are 5/6 in total. So it's a half plus 2/6, which is a third, which equals 5/6. But of course there's a problem here because I've double counted this 6. It's actually achieved A and B. If I roll a 6, then I've achieved A, and if I roll a 6, I've also achieved B. So I can't double count it. I can't count this as two different events because it's not two different events. Even though it satisfies A and it satisfies B, it's still only one event. There's still only one way to get a sixth. So that's why I have to subtract this one here. I can't include that because then I'd be double counting. So the probability, if I roll a normal six-sided die that I get either an even number or a multiple of 3, is a half plus a third, which is probability of A, plus probability of B, minus a sixth, minus probability of A and B. And of course that equals 4 over 6 or 2 over 3. Okay, and that makes sense because what you can see in the diagram is that there are 4 different outcomes that would satisfy that I got an even number or a multiple of 3, okay? Now I'm going to quickly go through mutually exclusive events. So 2 events are mutually exclusive if they can't coincide. Coincide means happening at the same time. So 2 or more events are mutually exclusive if they can't happen at the same time. So some examples would be, let's say I toss a coin. The 2 events that I get a head and I get a tail, they are mutually exclusive. Because if I toss a coin, I can't get a head and get a tail. You can probably think of heaps more. If I roll a die, I can't get an even number and an odd number. It can't rain today and not rain today. On your report, you can't get an A and get a B. For maths, that is. So all of these events that I've gone through are mutually exclusive. They can't happen at the same time. Now, there's an equivalent way of saying this. 2 events are mutually exclusive if and only if probability, I should call it 2 events A and B. So A and B are 2 mutually exclusive events if the probability of A and B occurring equals 0. There are no events in the intersection of A and B, okay? Now, what that means for our last formula is that if A and B are mutually exclusive, so I'm just going to write ME for short, then remember our formula was that probability of A or B equals probability of A plus probability of B minus the probability they both occur. Okay, so that was on the previous slide. So if A and B are mutually exclusive, then this guy here just equals 0. Okay, that's what I just said. So then, the probability of A or B occurring, we can ignore this last part. The probability of A or B occurring is just the sum of the probabilities. Probability A or B equals probability of A plus probability of B. So, an example, if I do toss a coin, the probability that I get a head or tails is just the probability I get a head plus the probability I get a tail, which is 1, okay? So if I toss a coin, the probability I get head or tails is 1. That's common sense because it's certain that I will get a head or a tail. Okay, so it's very similar to the previous rule. It just makes it a little easier. So now we're going to look at independent events. Okay, so 2 events are said to be independent if either one of them occurring does not affect the chances of the other. So that sounds a bit complicated, but when we go through examples, it'll become a bit clearer. So basically, the chances of each don't affect each other. So I'll give you some examples. So let's say I toss 2 coins, and the first one is heads. Whatever I get on the second coin is independent of the first. So the 2 tosses are independent. The reason is, it doesn't matter if I got a head in the first toss, the chance of getting a head in the second toss is still a half. Some more practical examples, I guess you'd say. The weather in Canberra and the weather in Seattle in America. They are independent events. Another independent event might be what you do on your Saturday night and what I do on my Saturday night. Those two don't affect each other. What I do on my Saturday night has no bearing on what you do, and vice versa. So they don't affect each other at all. So, why am I telling you this? Well, the reason is that I showed you a rule for calculating an OR probability, A or B. There's a rule for calculating an AND. So the probability of A and B, remember this symbol means intersectional AND, is probability of A times probability of B. Okay, so I gave you an OR rule, this is an AND rule. But this rule only works if and only if A and B are independent. Now, there isn't actually a rule for calculating the probability of A and B if A and B are dependent. Okay, so you don't have to worry about that now. So, to give you examples of dependent events, so any two events that are mutually exclusive are dependent, because if one happens, it affects the other one. It means it can't happen. Other dependent events, so say the Broncos winning this weekend and winning next weekend, they're not independent because they do affect each other. Sometimes it does get a bit subjective. So, for example, what I have for lunch and what you have for lunch. Now, you could consider them independent, but then again, you could consider them dependent, because if I, go to the canteen and I get myself one of those hot dogs, then there is less of a chance that you will be able to get a hot dog because they may run out or something like that. But most of the examples we're going through are clear-cut. So, when you're asked to find the probability of A and B, the two events A and B must be independent. So I'll give you an example, and I'll do it with a circle. So let's say that I'm going to toss 2 coins, like I was talking about before. So the probability that I get a heads is half, right? So I'm going to cut this circle in half. So this side can be heads and this side can be tails. So the probability on the first toss I get a heads is a half. That's clear cut. Now, if I do get heads on the first toss, the probability I get heads on the second toss is also a half. So, the probability I get heads and then another heads is going to be a half of a half, which is a quarter. So, I toss 2 coins, probability of 2 heads is half times a half, or half of a half, which equals a quarter, which is the area shaded in black of the circle above. Now, independence does get a bit tricky. So let's say, for example, that I was going to draw 2 cards out of a normal 52 card deck. Okay? So let's say I want to find the probability that I get an ace and then another ace. Now, the thing is here, if I take an ace out of the deck the first time and I don't put it back, then of course there is less chance that I get an ace in the second pick, right? But once I take that ace out, I'm left with 51 cards and 3 aces. And then what I pick out of those 51 cards is independent of the first. So let's say I take the deck of cards and I pick out, and I want to find the probability, I pick 2 aces. So on my first go, there are 4 aces out of 52 cards, or 1 over 13. But then, if I don't put the ace back, there are 3 aces left, and there are 51 cards left in the deck. Now these two are independent events. So once I've taken the first ace out, there are 51 cards left, and 3 of them are aces. It won't matter that I picked an ace out of the first one. The probability of getting an ace the second time is still 3 over 51. So the probability that I pick 2 aces, one after the other, without replacement, will just be 4 over 52 times 3 over 51. And this just equals 1 over 221. So it's very, very unlikely. Okay, I know that this was very tricky stuff, so please ask if you have any questions. Other than that, this has been the luckiest maths teacher in the world. Have a great day.